Welcome! This week I will go over autocorrect. It is how your misspelled words are corrected automatically to the right ones. You know it's already from your email client on your phone. Let me show you how it works.
So let's go over this week's learning objectives. You'll learn about autocorrect conceptually. You've most likely used it in your phone or word processor. But what is autocorrect exactly? It can mean slightly different things depending on the context. You'll learn about the nuances this week. You will practice building a model to perform autocorrect. You will learn each step in autocorrect and key concepts to prepare you for the coding assignment. When performing autocorrect, you'll want to be able to quantify how far apart or different two strings are, and ask how many letters you can change to go from one string to another. To do this, you will learn to measure minimum edit distance. You will implement a really interesting algorithmic approach for solving the minimum edit distance called dynamic programming. At the end of the lecture, you'll demonstrate your new skills and put all these techniques to work in this week's assignment.
Exciting content! I'm looking forward to tell you everything about how you will be building your autocorrect. One very important concept is that the autocorrect you will be building uses dynamic programming. This comes up again and again in technical interviews. But first, let's get started with an overview of autocorrect in the next video.
Good job in learning this week's materials! You now know how dynamic programming works, and you can see why it is a very powerful algorithm. Just like how you can use dynamic programming to find the minimum edit distance between two strings, you can also use it to find the shortest path from point A to point B to point C, like in Google Maps. These are some very powerful models that you learned. In this week's programming assignment, you will be implementing autocorrect, and by the end of the assignment, you will be able to feed in a typo to your model, and it will give you the most likely correction. Autocorrect these days uses a lot of techniques, but you will get a good baseline and understand how the concepts work. You will also learn about dynamic programming in the assignment. Next week, you'll tackle part of speech tagging. Good luck in the assignment!
Now you know what states are. In this video, we're going to introduce parts of speech tags. In other words, you will see how you can go from one state to another state. In doing so, we will define a term that we call transition probabilities. These transition probabilities tell you about the chances of going from one POS tag to another.
If you think about a sentence as a sequence of words with associated parts of speech tags, you can represent that sequence with a graph, where the parts of speech tags are events that can occur, depicted by the states of our model graph. In this example, NN is for nouns, VB is for verbs, and other stands for all other tags. The edges of the graph have weights or transition probabilities associated with them, which define the probability of going from one state to another. There is one last important property that Markov chains possess, the so-called Markov property, which states that the probability of the next event only depends on the current event. The Markov property helps keep the model simple by saying all you need to determine the next state is the current state. It doesn't need information from any of the previous states. Going back to the analogy of whether water is in solid, liquid, or gas state, if you look at a cup of water that is sitting outside, the current state of the water is a liquid state. When modeling the probability that the water in the cup will transition into the gas state, you don't need to know the previous history of the water, whether it previously came from ice cubes or whether it previously came from rain clouds. That makes sense, right? Let's revisit the sentence example from earlier. If you look at this sentence again and want to know the probability that the next word following learn is a noun, then this just depends on the current state that you're in. In this case, the verb state, denoted by VB, because the current word learn is a verb. So the probability of the next word being a noun is the transition probability for going from the verb to the noun NN state. The transition probability is written on the arrow that goes from VB to NN, and as you can see, it's 0.4. You can also use a table to store the states and transition probabilities. A table is an equivalent but more compact representation of the Markov chain model, and this table is called a transition matrix. A transition matrix is an n by n matrix, with n being the number of states in the graph. Each row in the matrix represents transition probabilities of one state to all other states. For example, the first row represents the case where the current state is a noun. The columns represent the possible future states that might come next. The values inside the table represent the transition probability of going from a noun to a noun, from a noun to a verb, and a noun to some other state. Notice that for all the outgoing transition probabilities from a given state, the sum of these transition probabilities should always be 1. Equivalently, in the transition matrix, all of the transition probabilities in each row should add up to 1. Some of you may have noted one little flaw in this model. It doesn't tell you how to assign a part of speech tag to the first word in the sentence. This is because all of the states in the model correspond to words. But what do you do when there is no previous word, as in the case when beginning a sentence? To handle this, you can introduce what is known as an initial state by you include these probabilities in the table A. So now it has dimensions n plus 1 by n. Notice that the transition matrix can be written as an actual matrix, like this. To recap, Markov chains consist of a set Q of n states, Q1 all the way to Qn. The transition matrix A has the dimensions n plus 1 by n, with the initial probabilities in the first row. Nice work so far. I'll see you later.
In this video, you learned about initial probability distributions and you learned about transition probabilities. In the next video, you're going to learn about hidden Markov models, which are used to decode the hidden states of a word. In our case, that would be the parts of speech of that word. To populate the transition matrix, you need to calculate the probability of a tagging happening, given that another tag already happened. You also need to calculate the probability that a tag happens at the beginning of the sentence. You'll also learn about a new concept known as smoothing. So let's get started.
Begin by filling the first column of your matrix with the count of the associated tags. Remember, the rows in the matrix represent the current state, and the columns represent the next state. The values represent the transition probabilities of going from the current state to the next state. The state for this use case is the parts of speech tag. As you can see, the defined tags and the elements in the corpus are marked with corresponding colors. For the first column, you'll count the occurrences of the following tag combinations. As you see here, a noun following a start token occurs once in our corpus. A noun following a noun doesn't occur at all. A noun following a verb doesn't occur either. A noun following an other tag, O, occurs 6 times. The rest of the matrix is populated accordingly, but I'll take a little shortcut. The corpus, as you can see, is a verbless haiku. Because there are no tag combinations with the tag VB, they are all 0. Unfortunately, there's no such shortcuts in the programming assignments. You've been warned. The 0 tag, the O tag, following a start token occurs twice. The O tag following a noun tag, NN, occurs 6 times. And the last entry in the transition matrix of an O tag following an O tag has a count of 8. In the last line, you have to take into account the tagged words on, a, wet, comma, and comma back to calculate the correct count. Now that you have calculated the counts of all tag combinations in the matrix, you can calculate the transition probabilities. So far, you've calculated and entered the counts in the matrix, which corresponds to the numerator in our formula. Now, you just have to divide each count by the sum, which is actually the corresponding row sum. Remember what this row sum represents. For the row where the current state is a noun part of speech, the sum across that row represents all pairs of words where the current state is a noun, and the next state is any part of speech, whether it's a noun, a verb, or other. So for the transition probability of a noun tag NN following a start token, or in other words, the initial probability of a NN tag, we divide 1 by 3. Or for the transition probability of an other tag followed by a noun tag, we divide 6 by 14. You may have realized that there are two problems here. One is that the row sum of the VB tag is 0, which would lead to a division by 0 using this formula. The other is that a lot of entries in the transition matrix are 0, meaning that these transitions will have probability 0. This won't work if you want the model to generalize to other haikus, which might actually contain verbs. To handle this, change your formula slightly by adding a small value epsilon to each of the counts in the numerator, and add n times epsilon to the divisor such that the row sum still adds up to 1. This operation is also referred to as smoothing, which you might remember from previous lessons. So if you substitute the epsilon with a small value, say 0.001, then you'll get the following transition matrix. The values shown here are shown up to the third decimal digit, so don't worry if the row sums don't add up to 1 exactly. The result of smoothing is, as you can see, that you no longer have any zero-valued entries in A. Further, since the transition probabilities from the VB state are actually 1/3 for all outgoing transitions, they are equally likely. That's reasonable, since you didn't have any data to estimate these transition probabilities. One more thing before you go. In a real-world example, you might not want to apply smoothing to the initial probabilities in the first row of the transition matrix. That's because if you apply smoothing to that row by adding a small value to possibly zeroed valued entries, you'll effectively allow a sentence to start with any parts of speech tag, including punctuation.
You just learned about smoothing and saw why it is important. That is great. Now in the next video, we will move on and see how you can populate another type of matrix, known as the emissions matrix. Hello. I will now show you how you can initialize a matrix that can tell you the part of speech tag of every word. This matrix will tell you the probability that every word belongs to a certain part of speech tag. Let me show you how you can do this.
As you just saw, the initialization step is one of 3 steps to populate the auxiliary matrices C and D. In the initialization step, the first column of each of our matrices, C and D, is populated. The first column of C represents probability of the transitions from the start state pi in the graph to the first tag Ti and word W1, meaning we're trying to go from tag 1 to the word W1. This is shown here for a model with 3 hidden states, for the sake of clarity. So the first column entries, Ci, 1, are the product of the transition probabilities of the initial state and the respective emission probabilities. As your initial probabilities are contained in the first row of the transition matrix A, this is the same as A1, I times the corresponding emission probability B. The C-index function simply returns the column index in the matrix B for the given word, here W1. In the D matrix, you store the labels that represent the different states you're traversing when finding the most likely sequence of parts of speech tags for the given sequence of words W1 all the way to WK. In the first column, you simply set all entries to 0, as there are no preceding parts of speech tags we have traversed. That's it for step 1.
You now know how to initialize your matrices. In the next video, you're going to learn how to continue populating your matrices, and you can use that to decode the parts of speech of a certain sentence. You'll learn about the Viterbi algorithm, which you can use for parts of speech tagging and also speech recognition.
Welcome to week 3. This week is all about autocomplete, which is a technology that you use on a day-to-day basis. If you open up your email or a text document, you will see that you can often autocomplete your sentences. Some startups are working on autocomplete for code editors. Isn't that cool? Imagine a software that can help you do this week's assignment. Autocomplete is a very popular tool. When you Google something, you often have suggestions to help you complete your search. If you are building a web app, it would be nice to have autocomplete for some suggestions. This week, you'll be implementing n-gram models. A language model assigns the probability to a sequence of words in a way that more likely sequences receive higher probabilities. For example, the phrase I have a pen is expected to have a higher probability that I am a pen, since the first one seems to be a more natural sentence in the real world. You can take advantage of this probability calculation to develop an autocomplete system. Jonas will show you how.
Yes, let's do this. In this video, I'll show you how to evaluate a language model. The metric for this is called perplexity, and I'll explain what this is.
First, you will divide the text corpus into train, validation, and test data. Then, you will dive into the concept of perplexity, an important metric used to evaluate language models. So, how can you tell how well your language model is performing? Recall from the previous videos that a language model assigns a probability to each sentence. The model was trained on a corpus, so for the training sentences, it may assign very high probabilities. You should therefore first split the corpus to have some testing and validation data that are not used for the training. As you may have done in the other machine learning projects, you will create the following split of training, validation, and test sets. The training set is used to train your model. The validation set is used for things like tuning hyperparameters, and the test set is held out for the end, where you test it once and get an accuracy score that reflects how well your model performs on unseen data. A commonly used split for smaller datasets is 80-10-10, or 80% to training, 10% to validation, and 10% to testing. In a very large dataset, such as text analysis, testing could make up as little as 1% of your training set. In NLP, there are two main methods for splitting. You can split the corpus by choosing longer continuous segments like Wikipedia articles, or you can randomly choose short sequences of words, such as those in the sentences. Now that you've split the dataset, you can evaluate the test sets using the perplexity metric. Perplexity is a commonly used metric in language modeling. But what does it mean? If you're familiar with the word perplexed, you know that a person is perplexed when they are confused by something very complex. You could think of perplexity as a measure of the complexity in a sample of texts, like how complex that text is. Perplexity is used to tell us whether a set of sentences look like they were written by humans rather than by a simple program choosing words at random. A text that is written by humans is more likely to have a lower perplexity score. On the other hand, a text generated by random word choice would have a higher perplexity. Let me show you how to calculate the perplexity of the model. You'll start by computing the probability of all sentences in your test set, and then raise the probability to the power of -1 over m. Perplexity is basically the inverse probability of the test set normalized by the number of words in the test set. So the higher the language model estimates the probability of your test set, the lower the perplexity is going to be. As a side note worth mentioning, perplexity is closely related to entropy, which measures uncertainty. Let's look at an example of two language models that are going to return different probabilities for your test set W. There are 100 words in the test set, so m is equal to 100. The first model returns a 0.9 probability of the test set, which is very high. This means that the first model predicts your test sets very well, so the model is highly effective. As you can see, the perplexity for that model and test set is about 1, which is very low. The second model returns a very low probability for your test set, 10 to the power of -250. For this model and test set, the perplexity is equal to about 316, which is much higher than the first model. So one thing to remember is that the smaller the perplexity score, the more likely the sentence is to sound natural to human ears. For context, good language models have perplexity scores between 60 to 20, sometimes even lower for English. Perplexities for character level language models, where you track characters instead of words, will be lower. Now we get ready to calculate perplexity for bigram models. In a bigram model, you calculate the product of bigram probabilities of all sentences. Then, take the power of -1 over m. Recall that the power of negative 1 over m of the probability is the same as the mth order root of 1 over probability. One thing to notice here is that in the case of the same probability for different test sets, the bigger the set m is, the lower the final perplexity is going to be. If all sentences in the test set are concatenated, the formula can be simplified to the product of probabilities of bigrams in the entire set. One other thing to note is that some papers use log perplexity instead of perplexity. So the perplexity formula changes from the mth order root of 1 over probability to 1 over m times the sum of the logarithms of the probabilities of words. This is easier to compute, so it's not uncommon to find researchers reporting the log perplexity of language models. Note that the logarithm to the base 2 is typically used. In a good model with perplexity between 20 and 60, log perplexity would be between 4.3 and 5.9. Now, how does the improved perplexity translate in a production quality language model? Here's an example of a Wall Street Journal corpus. If you take a unigram language model, the perplexity is very high, 962. This just generates words by their probability. With a bigram language model, the text starts to make a little more sense. Using a trigram, you can see the language it produces is pretty close to reasonable. The perplexity is now equal to 109, much closer to the target perplexity of 20 to 60 I mentioned earlier. Later in the specialization, you'll encounter deep learning language models with even lower perplexity scores.
You now understand what perplexity is and how to evaluate language models. To use them for real tasks, we will need to be able to handle words that did not occur in the training set. I'll show you how to do that in the next video. Congratulations for making it all the way here. In this video, we're going to do a quick recap of everything you learned and highlight the main takeaways. So for that, you have seen n-gram language models, computing probabilities, and handling text. Let's take a look at the overview in more detail.
Let's take a moment to reflect on everything you accomplished this week. You began with the definition of n-grams and how to calculate their probabilities from a corpus. Then you combine the n-gram probabilities to approximate the probability of a sentence. Organizing information about all n-grams in the corpus helped you to build a language model, a tool that estimates the probability of any sentence. You also resolved situations where information about some parts of the sentence was missing. You handled this in several ways: by transforming your model to deal with outs of vocabulary words using special unc-word, and by applying several methods to handle missing n-grams in the corpus, such as smoothing, backoff, and interpolation. Finally, you acquired a tool to help you choose the best language model for your task, the perplexity metric. Now, you're ready to take on your assignment, sentence autocomplete. You've done amazing work this week, and I hope you've enjoyed it. Best of luck on your assignment, and I'll see you later.
You have gone a long way and you learned a lot of important concepts in this week. N-grams are foundational and allow you to get a better understanding when you go into more technical models later in the specialization. The programming assignment will strengthen your understanding of this concept. Good luck and see you next week! When creating word embeddings, the corpus you are using to create them will affect your word embeddings. This is something we will explore later in the weeks. But first, let us see what is required to create these embeddings.
To create word embeddings, you always need two things: a corpus of text and an embedding method. The corpus contains the words you want to embed, organized in the same way as they would be used in the context of interest. For example, if you want to generate word embeddings based on Shakespeare, then your corpus would be the full and original text of Shakespeare, and not study notes, slide presentations, or keywords from Shakespeare. The context of a word refers to what other words or combination of words tend to occur around that particular word. The context is important, as this is what will give meaning to each word embedding. A simple vocabulary list of Shakespeare's most common words would not be enough to create embeddings. The corpus would be a general purpose sets of documents such as Wikipedia articles, or it could be more specialized, such as an industry or enterprise-specific corpus, to capture the nuances of the context. For NLP use cases on legal topics, you could use contracts and law books as the corpus. The embedding method creates the word embeddings from the corpus. There are many types of possible methods, but in this course, I will focus on modern methods based on machine learning models, which are set to learn the word embeddings. The machine learning model performs a learning task, and the main byproducts of this task are the word embeddings. For instance, the task could be to learn to predict a word based on the surrounding words in a sentence of the corpus, as in the case of the continuous bag of words approach that I will describe in the next videos that you will implement this week. The specific of the task are what will ultimately define the meaning of the individual words. I'll get back to this in one of the next videos. The task is said to be self-supervised. It is both unsupervised in the sense that the input data, the corpus, is unlabeled, and supervised in the sense that the data itself provides the necessary context which would ordinarily make up the labels. So the corpus is a self-contained dataset that contains both the training data and the data that enables the supervision of the task. Word embeddings can be tuned by a number of hyperparameters, just like in any machine learning model. One of these hyperparameters is the dimension of the word embedding vectors. In practice, this dimension typically ranges from a few hundred to the low thousands. Using higher dimensions captures more nuanced meanings but is more computationally expensive, both as training time and later down the line when using the word embedding vectors. This eventually leads to diminishing returns. Finally, to feed the corpus into the machine learning model, the contents of the corpus must first be transformed into a suitable mathematical representation, from words into numbers. The representation depends on the specifics of the model, but it is usually based on the simple representations that I presented in the previous video, such as integer-based word indices or one-hot vectors. In this video, you learned about high-level process to create context embeddings. For the next step, I'll introduce you to several word embedding methods, including the continuous bag of words approach that you'll be implementing in this week's assignment.
So far, we have learned a new term known as self-supervised learning. This term will show up again and again in the field of machine learning. It is a mix of unsupervised learning and supervised learning. Now in the next video, we will see some of the methods used for word embeddings. Given some context words, we need to feed them into a model and predict the center word. However, since we might have several words that are context words, we have to find a way to represent them. We also need to find a way to represent the center word. So let's take a look at how to do that.
So far, you've cleaned and tokenized a corpus and extracted the context words and center word from a window that slides across your prepared corpus. Now, you're ready to transform the center words and context words into a mathematical form that can be consumed by the continuous bag of words model. Let's start with the center words. For the sample corpus, which is the sentence, I'm happy because I'm learning, you first create a vocabulary, which is the set of unique words in the corpus. So here, you get a 5-word vocabulary: am, because, happy, I, and learning. You can now encode each word as a column one-hot vector, where each row of the vector corresponds to a word of the vocabulary. So 5 rows in total here. By the way, here the words corresponding to the rows are arranged in alphabetical order, but any other order would be fine. In this way, the vector for am will have a 1 in the row corresponding to am and 0 everywhere else. Because will have a 1 in the row for because and 0 in the other rows, and so on. This is how you will input the center words into the model. For the context words, you will create a single vector that represents the context from all of the context words. To create this vector for the entire context, take the average of one-hot vectors of each context word. For example, if the context words are I am because I, the one-hot vector for the individual words are 0, 0, 0, 1, 0 for I, 1, 0, 0, 0, 0 for am, 0, 1, 0, 0, 0 for because, and 0.00010 again for I. And their average is 1/4, 1/4, 0, half, and 0, which yields the vector representation of IM because I, to be used with the model. So for the first window, I'm happy because the final vector representations that you will actually use to train the continuous bag of words model will look like this. These are column vectors, by the way. I'm just writing them in a single row to make everything fit on the slide. And so on for the rest of the training dataset. By now you've concluded the preparation phase. Starting from the raw corpus, you now have data that you can use to train a continuous bag of words model. Congratulations! Up next, you'll examine the details of this model and get ready to apply your new skills to this week's assignment.
Since you have fully represented the context words and center word each as a vector, you are now ready to learn more about the model. In the next video, we will learn about the architecture of the Seebaugh model. Sometimes, I find it easier to understand how models work by looking at their dimensions at each step. I personally find it easier to follow along the equations while keeping the dimensions in mind. So I thought this would help you too. Let's take a look at the dimensions of the layers at each step of the model.
You just saw the architecture of the continuous bag of words model and the vectors and matrices that are involved to make calculations on it. Now, I'll introduce you to the dimensions of these vectors and matrices. Here's the architecture of the neural network again. First, the input layer is represented by lowercase x, a column vector with v rows, where capital V is the size of the vocabulary. To get the values that will be stored in the hidden layer, you first calculate the weighted sum of the values from the input layer and add the bias. So W1 times X plus B1, and I'll call the result Z1. Lowercase h refers to the column of values stored in the hidden layer. To get h, you pass the values of Z1 into a ReLU activation. So in terms of dimensions, W1, the weighting matrix between the input layer and the hidden layer, has n rows and v columns, where n is the size of the word embeddings. B1, the bias vector for the hidden layer, has one row for each neuron in the hidden layer, so n in total. So when you multiply W1 by x and add the bias vector B1, you get a column vector with n rows, and passing it through ReLU preserves the dimensions. So as expected, the hidden layer is represented by a column vector with n rows. Next, to get the values of the output layer, you first need to calculate the weighted sum of the values from the hidden layer and add the bias, so W2 times H plus B2, which I'll call Z2. The values in Z2 are sometimes referred to as logits. To get the output y hat, you pass the values of the Z2 logits through a softmax activation function. Again, you'll see details of the activation functions later in the lecture. W2, the weighting matrix between the hidden layer and the output layer, has v rows and n columns. B2, the bias vector for the output layer, has one row for each output neuron, so v rows. When you multiply W2 by the vector for the hidden layer H and add the bias vector B2, you get a column vector with v rows. And again, no change when you pass it through softmax activation. So finally, you get the output column vector y hat with v rows. If you had a situation where, instead of column vectors, you're working with row vectors, then you'll need to perform the calculations with transposed matrices and inverted terms in the matrix multiplication. So for instance, instead of calculating h equals w1 times x plus b1, as you did with the column vectors, if x and b1 are row vectors, then you would calculate x times w1 transposed plus b1 to get z1 and then h as a row vector. Next, I'll show you how to use the neural network with batches of several examples instead of just one example at a time.
Now that you know the dimensions, this will help you in your programming assignment. Hopefully, you'll not get the famous dimension mismatch anymore. Let's look into this model a little bit more in the next video. I'll now show you the cost function for the softmax. You'll understand why it is a cost function and you'll see why you are learning it. You basically have to predict one of the possible words. In order for you to be able to predict one of these v possible words, you need to minimize a certain cost function. In this video, you'll understand what cost function you are minimizing and why you're doing that. So let's take a look.
Consider a machine learning model, a single training example made of an input and a true target, and the value predicted by the model based on the input. It has a loss function which measures the error between the prediction and the true value for a single input training example. With the continuous bag of words model, for a set of input context words represented by vector x, for which the actual value is the vector y that represents the actual center word. The prediction is the vector y hat. The objective of the learning process is to find the parameters that minimize the loss given the training dataset. In the case of the continuous bag of words model, the parameters being adjusted by the learning process are the weighting matrices W1 and W2, and also the bias vectors B1 and B2. The loss function you'll be using is the cross-entropy loss. I won't get into the theory. You should just know that the cross-entropy loss function is often used with classification models, which often go hand in hand with a softmax output layer in neural networks, just like the one you're using in the continuous bag of words model. If you've already worked with logistic regression, you probably already know a simple form of the cross-entropy loss function, aka log loss, when there are just two classes. With the notation I used for the continuous bag of words model, the formula for cross-entropy loss for a training example is J equals the negative of the sum over K from 1 to V of yk times the log of y hat k. As an example, consider the input context words I am because I, where the actual center word is happy. The corresponding vector is this vector y with a 1 in the row corresponding to the word happy. The prediction could be this vector y hat. As the largest value is in the row corresponding to the word happy, this vector would be interpreted as predicting happy as the center word, which is the correct prediction in this case. So let's calculate the cross-entropy loss. The log of y hat is this vector. Multiplying each element by the corresponding element of y gives us this vector, and I'm using the circle dot to denote element-wise multiplication. Note there is only one non-zero value, which is negative 0.49. The sum is therefore this value, and the loss is minus the sum, so 0.49. Now, what if the prediction was wrong? Say that the predicted vector was 0.96, 0.01, 0.01, 0.01, predicting am instead of happy. The log would be this vector. Multiplying element-wise by y would give us this vector. Then the sum is negative 4.61, and the loss is negative 1 times this, so positive 4.61. So you can see that the loss is larger when the prediction is incorrect. More generally, the cross-entropy loss boils down to negative 1 times the log of the value of the prediction element corresponding to the actual center word. So if you plot the cross-entropy loss as a function of the value of the prediction for the actual center word, you can see that if the model is predicting correctly with a y hat value closer to 1, then the loss will be closer to 0. This is because log of 1 is equal to 0. If, on the other hand, the model is predicting incorrectly, then the y hat for the actual word will be closer to 0, resulting in a high loss value. The reason for this is that the limit of log x as x approaches 0 is minus infinity. So for the loss, which uses negative 1 times the log, as y hat approaches 0, the loss approaches positive infinity. So the loss is rewarding correct predictions and penalizing incorrect predictions.
You have computed the cross-entropy loss for one training example and have seen the plot of the cross-entropy loss versus the actual prediction. In the next video, we will be looking at the forward propagation of the Seebaugh model. Once you are done training your model and have optimized the cost function, you still need to actually get the word embeddings. In this video, I will show you several methods to extract the word embeddings from the weights learned by your model.
You have already implemented forward propagation, back propagation, and gradient descent to train the neural network of a continuous bag of words model. But how do you get the word embeddings out of your trained neural nets? As you may remember, word embeddings are not directly output by the training process. They are a byproduct of the process. I'll now explain how you can extract word embeddings from a trained neural net. Remember, these are vectors that carry the meaning of the words of the vocabulary, based on the context words in the corpus. Once you've trained your neural network after iterating through all of your training data, possibly several times, you can extract three alternative word embedding representations. The first possibility is to consider each column of W1 as the column vector embedding vector of a word of the vocabulary. Recall that matrix W1 has V number of columns, so it has one column for each word in the vocabulary. The mapping between columns of W1 and words uses the same order as the input rows. For example, with the corpus I am happy because I'm learning, if the 5 rows of the input vector or matrix corresponds to am, because, happy, I, and learning, then in W1, the first column will be the word embedding column vector for am, the second for because, and so forth. The second option to extract word embeddings is to use each row of W2 as the word embedding row vector for the corresponding word. Matrix W2 has V rows, one row for each word in the vocabulary. Again, the order is the same as the input vector or matrix. So with our sample corpus and input, the first row would be the word embedding row vector for am, the second for because, and so on. The third and final option is to take the average of the two previous representations. So if you want word embedding column vectors, you would average W1 and the transpose of W2 to obtain W3, a new n by V matrix. You can then extract the word embedding vectors from each column of W3 as you did previously. So with our visual example, the word embedding for am would be the first column of W3, which would be the average of the values of the first column of W1 and of the first row of W2. In this week's assignment, you'll be averaging W1 transposed and W2 to extract the word embeddings as row vectors.
Now that you know how to train these word vectors, in next week's video, you'll learn how to test them. Specifically, you'll learn about two types of evaluation metrics. The first type is intrinsic evaluation, and the second type is extrinsic evaluation. The two types of evaluation metrics are intrinsic evaluation and extrinsic evaluation. Depending on the task you're trying to optimize for, you can choose one of them. So let's dive in.
Allow me to introduce intrinsic evaluation. Intrinsic evaluation methods assess how well the word embeddings inherently capture the semantic or syntactic relationships between the words. Semantics refers to the meaning of words, whereas syntax refers to the grammar. You could do this by testing the word embeddings on analogies. You could test semantic analogies, as in finding the missing word in France is to Paris, as Italy is to blank. You could also evaluate the embeddings on syntactic analogies, such as plurals, tenses, and comparatives, as in seen is to saw, as been is to. One consideration you should be aware of for this approach is that there could be several possible correct answers, as in wolf is to pack, as bee is to blank, where the collective noun and missing word could, for instance, be swarm or colony. Here's an example from the original Word2Vec research publication, with the word embeddings created from a huge training set. I should mention that the word embeddings were created by a continuous skipgram model, and not a continuous bag of words model. But the evaluation principle is the same. Note that the analogies are not perfect. For example, the word embeddings fail to completely capture the relationship between chemical elements and their symbols. The symbol for copper is Cu, the symbol for zinc is Zn, the symbol for gold is Au, the symbol for uranium is U, but the Word2Vec embedding outputs the word plutonium instead of U. You could also perform intrinsic evaluation by using a clustering algorithm to group similar word embedding vectors, and determining if the clusters capture related words. This could be automated using a human-made reference, such as a thesaurus. Here's a visualization of clusters taken from a paper on the evaluation of word embeddings. If you look at the word cluster, you can see that the words fight and agitate are close to each other. Similarly, the word hair care and hairdressing are also close to each other. Interesting, right? In this week's assignment, you'll visualize the word embedding vectors, which qualifies as a basic intrinsic evaluation of the vectors that rely on human judgment to assess the quality of the embeddings. But first, I'll show you one more approach to evaluate the quality of word embeddings: extrinsic evaluation.
So here is a recap of what you have learned. Intrinsic evaluation allows you to test relationships between words. You can use for clustering, analogies, and visualization. In the next video, you'll learn about something slightly different, known as extrinsic evaluation.
That was a lot of content for a week. In this week's assignment, you will practice how to compute word embeddings. For example, to implement sentiment analysis, you can go beyond counting the number of positive words and negative words. You can find a way to represent each word numerically by a vector, and then the vector can represent syntactic and semantic structures. These vectors are the one that you will get from training the continuous bag of words model. By completing this assignment, you will train word vectors from scratch, learn how to create batches of data, understand how backpropagation works, and finally plot and visualize your learned word vectors. In the next course, we will move from probabilistic models to sequential models. Good luck with your programming assignment.